This video is about the Collatz conjecture, which goes by several other names, including 3n plus 1, 3x plus 1, the hailstone sequence, and many others. In particular, this is a summary of my proof. This is so that you can look at it quickly and decide whether you want to look at the full paper or not. So this is the Collatz iteration sequence. You start from somewhere, you pick a number. If the number is even, you divide it by 2. Otherwise, you multiply it by 3 and add 1, hence the 3n plus 1 part. And you keep going around and around in this loop until you either terminate or something else happens. So the question is, does this sequence always terminate for any n? The Collatz conjecture says yes, this sequence terminates for all n. For any given starting value, it can either terminate, in other words it reaches 1, or it can iterate round, going around and never getting anywhere, off to infinity, or it iterates to somewhere but gets stuck in some sort of infinite loop and therefore never terminates. So we've got two conditions here where it never terminates. Now we know that for all values up to 10 to the 20, which is pretty high, they've all been found to terminate, just using a brute force approach where you test every single value. Obviously this takes a lot of computing effort. 10 to the 20 is where we've got to so far, and 10 to the 20 is very small compared to the total amount of numbers that are available. Now, this is the structure table. Here, number 1, that's the termination point. In order to get there, you have to come through this yellow path, which is level 0. Now, you can either start from any of these even values. So, for example, if you start at 8, you iterate down 8, 4, 2 to 1. Or you have to come in from level 1. For example, 5 iterates to 16, 8, 4, 2 to 1. Any number in the structure table is necessarily going to terminate. For example, suppose we have 181 in level 7. 181 is going to go to 544, 272, 136, 68, 34, 17. This colour is different. I'm going to pretend that's not there. From 17 you jump over to 52, 26, 13, so you're coming this way to 40, then you come along here, this way, up there, terminate. So this is all very straightforward. This table is extremely difficult to draw because on here, level 3, I've only got one row, and there's as many rows in level 3 as there are level 2 values to get into. There are infinitely many starting values in the structure table, but that does not mean all values. Infinity and all is not the same thing. So any starting value in the structure table terminates. Okay, so this is labelled the stray table. So we suppose, for the sake of discussion, that there is some starting value p here which is awkward. It's not going to terminate. It does something else. Maybe it goes into a loop, maybe it just iterates off to infinity. If it exists, then there must be some value 2p above it, and if you start from 2p, you come down to p, and then you go off on your merry way and never terminate. So if there is a single starting value which does not terminate, then we've got an infinite column of values above, 3 dots, the ellipses carry on this way. It means that you can have some starting value up here which would iterate down, dividing by 2 till it reached p. So p is odd because we've divided by 2 until it is odd. it would iterate up to 3p plus 1 and then iterate down to some new value q. Q then goes along, iterates up to 3q plus 1, then comes down to some new value r. But you notice when I got q, I could come down into q all these different ways, and then I got into that chain from here, more 3 dots. So this was infinity, that's infinity, 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 there's infinities up. All of these are infinite. So in this one sheet here, I've shown loads of different infinities, and it carries on. So you cannot have a single value which doesn't terminate. You have to have an infinity of values that don't terminate, which is interesting. So we're not looking for a needle in a haystack, we're looking for an infinity of needles in a haystack. So we really need to understand what we mean by infinity. So it's not possible to have one awkward value. So we need a different way of counting than mathematicians normally tell you about. So if we have natural numbers up to a huge value h, there are h natural numbers there, from 1 to h. H upon 2 of them are even. So we can say that 1/2 of all natural numbers are even. But we're talking in a very special sense. You know, you can't halve infinity, so we need to talk about natural density. So this is a standard technical term, but it's not well publicized, so you don't find it in textbooks. Now, how about the set of perfect squares? Now, a perfect square is the square of an integer. So 9 is 3 times 3. So 9 is a perfect square. If we consider numbers up to h squared, so there are h squared natural numbers up to h squared, but only h of them are perfect squares. So that's only h out of h squared natural numbers are perfect squares. That's 1 over h. Now h increases without limit. So despite the fact there are infinitely many perfect squares, almost no natural numbers are perfect squares in this sense of natural density. So we have to keep saying in this sense of natural density throughout, because I'm going to say that 1/3 of numbers do this or 1/5 of numbers do this, and we're talking about all numbers. And you know, mathematicians don't like saying half of infinity. It doesn't really have any meaning. So we're saying we're talking about it in the sense of natural density, because we want to quantify. If you just say there's some sort of infinity of infinite chains, that's not quantitative, it's a bit wishy-washy. In much the same way that the infinity symbol is a bit wishy-washy. Now, so changing the subject slightly, we've got the negative Collatz sequence. Now, the Collatz sequence is only defined for positive integers. That's 1 upwards. But if we try using negative numbers, we get a more interesting pattern occurring. So this is what's called the Collatz outcome map. So starting from 1, I see where it iterates to. Now, I've cheated by saying you put a negative number in, you get a negative number out, and I'm suppressing the negatives. So when I say I'm starting from 1, I'm starting from -1 really. But the interesting thing here, if we come down a column, these are consecutive starting values. So it'll be 1, 2, 3, 4, down to I think about 60, and then you start again at the top. It doesn't really matter how you show this map. But the point is, they look fairly jumbled up, and there are 3 possibilities. We've got green, that terminates at 1. That would be a standard termination for the standard Collatz. But in the negative Collatz sequence, you get loops. So the blue and red are loops. So you start from a value and you loop forever. So this has got 3 possible outcomes. And the interesting thing about the negative Collatz sequence is, down here, if you could read it, there's 30% or 33% roughly for each of the possibilities. So previously we were talking about an infinity of infinities, and now we see that there was 3 possible outcomes and they're equally likely, and they seem fairly randomly distributed over this range. Now, I've investigated this up to much higher ranges, and you do get non-randomness occurring. So for example, you can get like clumps of blues and greens. So there is some sort of interesting pattern going on at higher values. You can't rely on it being 30% within any particular range of values, but nevertheless, over a big enough area, it does seem to be 30% each for the different outcomes. So now I want to talk about probability. Now, some people might go, oh, it's probability, that doesn't work for the Collatz. We can't look at probabilities. So you just have to bear with me for a while. I want you to consider a barrel containing 10,000 widgets. Plastic widgets. It's a big barrel. And they all should be blue. But some terrorist, a widgets right activist, has sabotaged at least one barrel by mixing in red widgets. So I want to say, if I sample the barrel, can I tell if my barrel is good? So to be clear, the barrel is in one of 2 states. It's either a good barrel, 100% blue, or it's only 90% blue. So the only way to establish if I've got a good barrel is to sample it. If the barrel is bad, we need to find it with extremely high confidence, which I'm going to say is equivalent to certainty. Now, if you take 10 samples and they're all blue, you're misled into thinking, oh, I've got a good barrel. But that's only 35%, which is a bit rubbish. If you take 100 samples from a bad barrel and all the samples turn out blue, that happens with 26 parts per million probability. So, you know, we're beginning to talk sense in terms of we're quite confident that if all the samples are blue, we've got a good barrel. But, you know, 26 parts per million, that's not very good. But now if we take 1,000 samples, random samples, so we, you know, shake the barrel up, the probability is now 1.75 times 10 to the minus 46. Now, for me, as an engineer, that is pretty much 0. And at that level, I would regard that as a certainty. Now, your mileage may vary. You might say, oh, look, if it's not absolutely 0, I don't believe it. Okay? Well, can't do anything about that. So, the basis of the proof. So, I've shown you where if you have any single starting value that fails to terminate, then you have to have an infinity of non-terminating starting values. Okay? So you can imagine looking for a needle in a haystack and you'd say, I've got no chance of finding it. You know, you can imagine sampling the range of numbers from 1 to 10 to the 20 and you'd say, well, there's no amount of samples I can take to find one bad terminating thing, one needle in the haystack. But that's not what you're looking for. You're looking for an infinity of needles and an infinity of bits of straw. And then you don't want to know now what's the ratio of those infinities. So the nature, the size of the infinity of non-terminating values is what we need to know. And that's difficult. But I then claim that with adequate sampling, which is going to come down to your acceptance level, you will find that you've got non-terminating starting values if they exist. So we're saying that if you don't find any, that is evidence that there are none. Now, That's not a standard proof, but this is a difficult problem. So let's see what evidence we've got for the proof. The positive, because I'm looking at structure tables which can be in the negative or positive Collatz, so I just have to prefix it now by saying the positive structure table apparently covers all possible starting values. I have not been able to prove that. The interesting thing is that the negative Collatz sequence has a structure table which is very similar to the positive one, and of course if I managed to prove that the negative structure table covered all possible starting values, I would be wrong, because we know only 30% of the negative Collatz sequence actually terminate. So it's symmetrical in the sense that I can't prove it for the positive one and I can't prove it for the negative one. Now, the straight table has exactly the same construction as the structure table. I mean, they look the same, how you form them. So the structure table, we say, fills out the infinite range of natural numbers, and the straight table does the same. So they both have to spread out, and somehow the tables are orthogonal. They're non-intersecting. I've proved that in the paper. If any value in the straight table is shared in the structure table, the straight table collapses. It gets absorbed into the structure table and doesn't exist. So it is certain and proven that the straight table exists. If it exists, it's of infinite extent. But this infinite is the tricky point. We need to quantify that infinity. 2 I will come back to. So, provided that the infinity of elements in the supposed straight table is a constant fraction of the starting values, so for example 30%, adequate sampling, whatever we consider that to be, will find it if it's there, and you can have an arbitrarily high confidence level. And if you can't find them, then that's evidence that they're not there. So this is the problem area. Well, this is the difficulty with pure mathematicians. Right? That's not a slur on pure mathematicians, but some will say 10 to the minus 40 is not adequate evidence. Okay, but if that same person then says, well, 10 to the minus 400 is not acceptable evidence either, well, I think we'd have to agree to differ on that. But, if the confidence level is 10 to the minus 400 probability, and you can't accept that as being proven, then, this is not the proof for you. Move along. So, we're now looking at the final point to consider. The natural density of the infinite set of possible non-terminating starting values. We've shown that it exists, if and only if non-termination is an actual outcome. So we're looking for something which may not exist. So that's kind of tricky. Now, in the negative Collatz sequence, we had 3. Termination at 1, there's a short loop, this one, and there's a longer loop. Now, my expectation was that the longer loop would have a bigger capture area. So, for example, only 10% would be on the short loop, and maybe 40% would be on the long loop. And surprise, surprise, each one of these has a 30% outcome density. In other words, if you pick 1,000 starting values, a third of them go to each type of termination, which I can't back that up with any analytic support. I can't come up with an equation. I couldn't come up with an equation which says that the infinity is any particular size, and I'm quite used to dealing with infinities and counting them, so that's quite upsetting, really. But it's not entirely unreasonable to suggest that all we've done is replaced one conjecture with another. So the Collatz conjecture says it terminates, and then the other conjecture is that there's this fractional outcome possibility. That's true in some sense, but on the other hand, we've got 3 identically constructed infinite tables in here. Those 3 construct infinities above them and they're all the same size. And, that's not a coincidence. So, the negative Collatz sequence is exactly the same as the positive in the sense of actual iteration sequence. So, it's pretty reasonable to suppose that if the positive Collatz has some sort of non-terminating outcome, it will also give a fractional type of infinity. And so that is a key supposition of the proof. Now again, if you don't accept that as reasonable, then there's no need to carry on, because that's the method. So now I've set this out very briefly. There's a fairly long papers, and they're quite slow and concentrated, and it's going to take some study to look at them and understand them. But if the overview, you look at it and go, well, I'm not going to be convinced by that ever, then you've saved yourself some time. You don't have to worry about it. But see, the thing is, the Collatz conjecture is known to be a difficult problem. It's infamous for being very simple to state, but impossible, literally impossible to prove. So we know mathematical induction, contradiction, standard proofs do not work. And mathematicians have said, mathematics is not up to this type of problem yet. So a new type of proof is required. Now, for my part, I didn't really know. Did I believe it or did I not believe it? Because 10 to the 20 is tiny compared to something like 10 to the 300. There's lots of numbers bigger than 10 to the 300. So there's plenty of scope for some non-terminating values to start up at, 10 to the 400. And then suddenly all things start going wrong. So that's possible, and we mustn't ignore that. But you've got to remember that brute force is around 10 to the 20. And people are spending computer time. There's obviously some reason that they're willing to spend their time looking around 10 to the 20 and above. So for version 1 of the paper, I push this up to 10 to the 37163. So I'm sampling up at this large range. Now that's ridiculously higher than where the current computational effort is. That's stupidly high. But, I thought about it a minute and I thought, there's going to be people who say that's not high enough. Because what I'm saying is, I'm confident that there are no loops and no things that don't terminate up to that value. But I can't say that there aren't any above that value. If there was a value at 10 to the 37164, I wouldn't see it. So I went mad and I said, right, I'm going to go up to this new value, 10 to the 371,641. So that's 300,000 orders of magnitude bigger. Now, that number is so stupid, it's ridiculous. It's hard to believe that numbers actually exist up there for any practical purposes. So I claim that for all practical purposes, remember I'm an engineer, Collatz conjecture is true for all natural numbers. So that is what the proof is going to say. Now, if you've seen the overview, the summary, and you say, well, I won't be convinced by any of that, then you save yourself some time. You don't have to bother reading the papers. It's a waste of time, because nothing is going to be presented which is anything other than what I've said so far. Now, what I've said so far may not be convincing. It's not convincing. You see, I've done a lot of simulations up to 10 to the 300. I've looked at the density of the plots and the outcome plots, different values, and you keep plugging away and you go, do you know what? It just doesn't seem that this is going to do anything. I could put in bigger numbers than this, and spend a few weeks doing the simulations, but I don't think, even at this value, 10 to the 371,641, if I pushed it up to some bigger number, put another 0 on the end of that, I don't think that would convince anyone any more than they are already convinced or not convinced. Another few orders of magnitude on top of that. It won't make the difference between being a believer or not. And, that is the nature of this proof. And if you don't like it, well, I can't do anything about that. I'm sorry. So these are the detailed papers what we're talking about. The inner structure of the Collatz iteration sequence. You'll notice there's version 1.6 now because I keep finding new things to tweak in it. It's not so much corrections but additions to improve it. And then the negative Collatz sequence is the final piece of the puzzle. So this one's quite old in terms of starting off in, well, that's 2021. Not that old. But the negative Collatz sequence, again, I tweaked that one slightly to add in some more references. There's a free bonus, free ebook, woohoo, all about the true mathematics of infinity, because frankly, infinity is quite a nice thing to handle if you do it properly. And if you do it badly, you get some really useless answers. So I've got this here. You don't need to read this to understand the Collatz proof, which you may not think is a proof. There's always subject to peer review. For me, it's a proof. For you, well, your mileage may vary. But thank you for taking your time to listen.